We have an exponential application problem here that we're going to be doing. Here it is. It's the population of Sasquatch in Bigfoot County is modeled by this particular equation, where P of t is the population of Sasquatch and t is the years after 2010. So it says find and interpret P of 0. So part A, we're going to find P of 0. That means I'm going to put in a 0 wherever I have a t. So 1 plus 3.167 e to the negative 0.05 times 0. So that means that my exponent on e is going to be 0. Anything to the 0 power is always equal to 1. So this right here is going to become 1. So then what I'm dealing with is 120 over 1 times this plus this. So that ends up being 4.167. Doing that on our calculator, we're going to come up with 28.8. And what does that mean? Well, P is the population of Sasquatch in T years after 2010. So that means that we're going to have 28.8 Sasquatch. Rounding that to the nearest full Sasquatch, it means that we're going to have, in 2010, there will be 29 Sasquatch. The second part of the problem says, find the population of Sasquatch in Bigfoot County in 2013. Round your answer to the nearest Sasquatch. Okay, so in 2013, t is going to be equal to 3. 2010 it was equal to 0. 2013 it's going to be equal to 3. So that means I'm going to put in a 3 wherever I have a t into my function. So I'm going to be finding P of 3. So when I put in 3 for t into my function, and then I simplify, I end up with 1 plus 3.167 e to the negative 0.15. And then I need to again do it on my calculator. So now when you remember, when you do these problems on your calculator, you need to tell your calculator what's in the numerator and what's in the denominator of your particular equation. So you need to make sure that your calculator knows what to put in. So I would put in 120 divided by, and then I would use a set of parentheses, 1 plus 3.167 e, and then automatically your calculator will put a parenthesis in there, negative 0.15. Close the parenthesis on my exponent on my e, and then I need to close the parenthesis on my division of 120. Doing that gives me about 32 Sasquatch in 2013. Part C says that they want me to find when the population is going to reach 60, and we're supposed to round to the answer to the nearest year. So that means that my population, my P, is going to be 60, and I need to set that equal to 120 over 1 plus 3.167 e to the negative 0.05 t. So what I'm going to try to do is get this exponential part of my equation by itself. First, I'm going to multiply both sides of the equation by the denominator here. So I'm going to end up with 60 times 1 plus 3.167 e to the negative 0.05 t equals 120. Using my distributive property here, I end up with 60 plus 60 times 3.167, which is 190.02 e to the negative 0.05 t equals 120. And remember, your goal is to get that exponential function by itself. So we're going to need to subtract 60 from both sides, and then we're going to need to divide both sides by 190. So subtracting 60 from both sides, we end up with 190.02 e to the negative 0.05 t equals 60. And then you still want to get that exponential function by itself, so we're going to divide both sides by 190.02. Now I'm going to have the exponential function by itself, e to the negative 0.05 t is equal to 60 over 190.02. Now that we have the exponential function by itself, we can rewrite it in logarithmic form. And to rewrite it in logarithmic form, the base of my logarithm is going to be the same as the base of my exponent, which happens to be e. So I can rewrite this as ln natural log of 60 over 190.02 equals negative 0.05 t. And then we're going to divide both sides by negative 0.05. And we end up with t is equal to the natural log of 60 over 190.02, all divided by negative 0.05. So t, using my calculator again, is approximately 23 years. So it'll take 23 years for the population of Sasquatch to reach 60. The last part says, find and interpret the end behavior of the graph y is equal to p of t. Check your answer using a graphing utility. So what we're going to do is we're going to take the original function, p of t, and as t gets very, very big, goes to infinity, this e function is going to be getting very, very small. Because remember, e to a negative exponent, let's just say t was equal to 1. So this is when t is equal to 1. This becomes 1 over e to the 0.05, which is a very small number. So as t gets bigger and bigger and bigger, this number is going to end up getting smaller and smaller. So let's just say, how about if a t is equal to 100? So now we would have e to the negative 0.05 times 100, which gives me e to the negative 5, which is 1 over e to the 5th. So believe it or not, if you were to put this on your calculator, 1 over e to the 0.05, this was approximately 0.9512. 1 over e to the 5th is 0.0067. So as we get bigger t's, my e's are going to get smaller and smaller and smaller. And they're going to get so small that we can just call them close enough to 0. They're just getting smaller and smaller. They're never going to equal 0, but they're going to be close enough. So that means that up here in this function, this exponential part of my function is going to approach 0. As t goes to infinity, e to the negative 0.05 t is going to go to 0. When I put that into my equation here now, my function, I'm going to have 120 over 1 plus 3.167 times 0. That ends up canceling that out, and I end up with 120 over 1, which means that my population, as time goes by, is going to max out at 120 Sasquatch. I'm not going to have any more than that, only 120. The environment will have way too many Sasquatch at that point, and it will not be able to sustain anymore. Then it said to look at check your answer using a graphing utility, and so I've done that. And when I used my graphing utility, this is what I came up with. And you can see that as time goes by, it starts to approach a horizontal asymptote. And just to verify that that's 120, I'm going to put y equals 120 into my calculator. So here's the graph of the Sasquatch population, and then the next graph you're going to see is a horizontal line at 120, and you can see that my graph is approaching 120. So the graphing utility agreed with what I figured out mathematically.